Hello, everyone. I would first like to thank you all for attending our talk. The title of our talk is Exploiting CSP in WebKit to Break Authentication and Authorization. Now, have you ever had an access to a zero-day bug which you could possibly use to take over accounts on any platform you want? No? Well, we kinda did. Today in this talk, we'll talk about a bug that enabled us to take over user accounts on most of the web applications out there. But first, a little bit about us. My name is Sachin Thakuri, and I'm a co-founder and security engineer at Threatnics, where I do mostly web and mobile security stuff. And I'm also a co-founder of ThreatCon, a security conference based in Nepal.
Hi, I'm Prakash. I'm a co-founder and security engineer at Rednix. I spend most of my time hacking web applications and sometimes playing with JavaScript and new browser APIs. In fact, this whole talk is based on a finding that we came across while playing with CSP Report URL.
Now, before we move on deep into the presentation, here's a quick TLDR version of the talk. Long story short, today we will discuss a vulnerability that was reported to Apple that Apple didn't consider severe enough to fix quickly, which then after waiting for a significant amount of time, we decided to exploit and earn some bounties by reporting them to bug bounty programs. The bug was in CSP implementation of WebKit, a browser engine used by Safari web browser, as well as all iOS web browsers, including Firefox and Chrome. The failure of WebKit to adhere to W3C specification when a CSP violation event is triggered leaked cross-site destination URL while redirecting from one origin to a different one. Combined this with common practice of implementing SSO's cross-site redirects to authenticate and authorize, we were able to steal codes, access token, or any other secrets that were part of the leaked URL, which we could then further use arbitrarily. This allowed us to carry out attacks, including but not limited to account takeovers, CSRF, and sensitive information disclosures. Moving on, now we will discuss few technologies and concepts before moving on to the vulnerability itself. SSO. Starting with SSO, have you ever seen these buttons where you can log in using Facebook or Google accounts on a third-party website and wondered how this works? These features work through a technology known as SSO. Single sign-on, also commonly known as SSO, is a technology that provides centralized authentication service. Generally, users are asked to provide their single set of credentials, and authentication to all other applications are verified through a centralized authentication service. Its ease of use and effectiveness has made SSO really popular among modern applications. In addition to being simple and easy to use, SSO is also considered more secure. SSO commonly works by generating an authentication token, which is then passed to other applications and services. Authentication token enables services to verify and authorize an identity, which is why securing and making sure that the authentication tokens are kept safely is of utmost importance.
Well, I assume we all know what CSP is, but let's just revisit it very quickly. Connectivity policy, or CSP, is a set of policy or rules defining how browsers should load resources like JavaScript or CSS or images, and whether to allow or deny use messages. It is defined using an SQL response header called connectivity policy, like shown here, and it can also be defined using meta tag with exclusions like report URI. CSP has been around since 2010 and is now supported by all modern browsers. We can also see it being widely implemented in Web 3.0 apps, and a lot of improvements happened over the years. Though setting the CSP header still seems to be a hard task because it depends on resources used on each particular page or site. That's why there is no standard recommendation or something as default CSP policy. I think it's not that uncommon to make mistakes while implementing a connectivity policy. And for that reason, we also have something called connectivity policy report only header. And what it does is, instead of actually executing the policy in action, it only reports violations, which makes it easier to debug if a policy is working as intended or not. So when it comes to CSP, we always have what we call violation reports because what if a user tries to load a restricted resource, right? In that case, browsers block the request and dispatch a violation report. And there are currently four ways of catching dispatch reports: CSP's report directive, report URI directive, report to, reporting observer, and security policy violation event. Throughout the talk, we'll be using security policy violation event for easier understanding. The report in general contains information on what caused the violation, like violated directive, blocked URI, or URI the user requested, and so on. I guess we all must have seen errors like this on our browser console, the image on the right. And that's basically a CSP violation report. And if you notice, it discloses the URL the user tried to load, that is evil.com. Though it's not that sensitive here, but it could be if it's a result of a redirect. And to avoid leaking such sensitive information, W3C recommends user agents only include the origin of the original request. The image on the bottom is from CSP 1.0, candidate recommendation from 2012. And even then, we had such cases covered. It says the violation reporting mechanism has been designed in a way to mitigate the possibilities of probing the behavior of another server. And it also explains why. That is, if a violation report contains the full block URL, the violation reporting report might contain sensitive information containing the redirected URI, such as session identifiers. And Sachin already explained, it's a typical case for SSOs and OAuth. And so it's a vulnerability and so on. However, if you notice, it recommends including the origin of the block URI, which is still an issue, and we have a long history of reports on that. Yeah, the first one from 2013 is by Igor Homakov when CSP was still in its infancy. He demonstrated what we could achieve by abusing CSP's block URI directly. This has been quoted directly from his blog post where it says, we can use CSP trick to detect if a user has authorized some apps or clients, because all authorized apps will redirect to their homepage instead of login or authorization page. For example, if you have already authorized Instagram on a Facebook account, sending a request to Facebook OAuth endpoint for Instagram would redirect to Instagram instead of Facebook. So yeah, that's the general case. And we've found several identical reports on Chromium issues looking origin of block URI in one way or another using CSP. We also found reports leaking full block URI in 2020, which were very similar to ours, and we'll talk about ours in later slide.
Now, after that history, let's discuss the root cause of the vulnerability. We can define a CSP policy in such a way that whenever a redirect happens to a domain with different origin, also known as cross-origin, a CSP violation occurs, and a security policy violation event is fired. As you can see in this figure, our domain cm2.pw with described CSP policy makes a fetch request to domain1.com. The response header from domain1.com contains a location header that now redirects to a domain with different origin, domain2.com. But due to our CSP policy, the request to domain2.com is blocked and a CSP violation event is fired. Now, when security policy violation event is fired, it uses security policy violation event interface at target with different attributes. While setting values of these attributes, a failure by WebKit to adhere to W3C specification resulted in leaking 3x redirection location in document URI attribute. As you can see in the example, fb.com/secretier redirects to facebook.com/secretier. Then you can see difference in values per attribute document URI set by Safari and other browsers. While other browsers who have followed specification mentioned by W3C seems to set value of a URI with values from where original fetch request was made, Safari, who failed to follow the W3C specification, set those values with final redirection URI. Now, you might be wondering how can this be exploited in SSO? Allow me to explain. As you can see in this figure here, when a user loads example.com, it first checks if the user is authenticated or not. And if the user is not authenticated, then as shown in the figure, it will send the user to auth.example.com, which is a SSO domain that provides centralized authentication. Now, after verifying the user is then redirected back to example.com with an authentication token. Now, the general common practice while implementing SSO is to use different subdomain or an entirely different domain, which then doesn't meet the criteria to be defined as same origin. So the final redirection that happens from SSO domain to the final domain are, in the case as shown in the figure, from auth.example.com to example.com will be cross-origin, thus allowing an attacker to steal the final redirection URL. In today's modern application, where authentication and authorization are heavily dependent on technologies such as OAuth, SSO, and JWT, where secrets are passed through URLs, the leak of the final redirection URL made applications using these technologies almost always vulnerable.
The responsible disclosure didn't go as we hoped it could. We first reported the vulnerability to Safari in 2020 and had to wait for a few weeks before we even received an automatic acknowledgement. After 2 months of waiting, we finally received a reply in April 20, and to our surprise, it said, "This doesn't seem to pose a threat to WebKit users." And it further went on to explain that even after fixing the issue, an attacker could gather the same information by monitoring WebKit logs while running an attacker-controlled build of WebKit. To us, it seemed as if they failed to understand the vulnerability and the risks it posed. Trying to convince them, the time went by, but we saw no progress at all. So in January of 2021, after waiting for almost a year, we decided to explore the potential of vulnerability in the wild by targeting bug bounty programs. And the exploit was simple. We set up a page with CSP as shown in the slide here, which what is the domain we're sending request to, an event listener for the reports a violation, and send a request. Sending a request to an authorization endpoint issues a redirect to another domain with code or token appended to the URL, which is typically the case, whereas this policy only allows loading of resources from the page itself and the domain specified, that is author.example.com here. So as Sachin said earlier, and time to load resources from any of the domains with valid policy and trigger the security policy violation event. And the document URI then would have the value of the actual doc URI containing the code or token. We've also prepared a playground for everyone to make it easier to experiment with the vulnerability. The usage is simple and pretty straightforward. You pass in a number of parameters as shown in the users on the left. The pet sets appropriate CSP policy using the domain attribute from the query string and displays the to-do as shown on the right. There we added an exploit button as a workaround for ITP, that is Intelligent Tracking Prevention, which Sachin will explain a little later. After a little wait, in the page issues a fetch request to the URL specified in the query string, which redirects to another domain, causing a CSP violation. The event listener then catches the event and will print the secret token on the screen. The source code for the playground is also on GitHub, so feel free to use as you please, or tweak or contribute however you want.
So now it's demo time. We have a short demo here, and this demo will demonstrate how an attacker can use this vulnerability to take over Instagram accounts. Now, after the demo, let's discuss impact. It took us a while to understand the full impact the vulnerability had. The vulnerability did not just affect Safari browser, but because of the Apple's App Store policies that states that apps that browse the web must use the iOS WebKit framework and WebKit JavaScript, which means that web browsers can't implement their own rendering engines. They must embed a version of Safari's rendering engine, which made browsers like Firefox, Chrome, Opera in iOS devices vulnerable. Due to the nature of design of OAuth, almost every implementation of OAuth that exists were vulnerable. Using the bug, we could take over Facebook, Instagram, and WhatsApp accounts. The bug also affected Google's SSO, which means Google products using Google accounts central authentication were also vulnerable. Cryptocurrency platforms, social networking platforms, e-commerce platforms, and more. In today's modern application, it's very rare to find an application not using OAuth. So let's just say the numbers were very high. Since the vulnerability affected SSO, so it's obvious that different SSO providers were also affected by this. And there are many different applications that make use of login with third-party features, such as login with Facebook or Google to provide the user with easy and seamless authentication experience. And since most of these features make use of OAuth, these applications implementing login with feature were also affected, thus allowing an attacker to take over accounts and platforms implementing these features. For example, let's say you have an e-commerce website where you have a feature that allows users to log in with Facebook account. Then an attacker could basically take over accounts of your users in your e-commerce website by stealing Facebook OAuth tokens. Moving on, let's discuss some roadblocks and common misunderstandings that we saw among security teams of different bug bounty programs that we reported the bugs to. Starting with ITP. ITP, or Intelligent Tracking Prevention, is a privacy feature developed and implemented by WebKit and has been in use since October 2017. ITP uses machine learning model to detect cross-site tracking capabilities, and it aims to reduce them by taking different actions such as full third-party cookie blocking, reducing the accessibility and longevity of first-party cookies, local storage capping and deletion, downgrading third-party referrals, and more. Due to the nature of the attack, where it relied on making third-party requests, ITP rendered the attack unusable on latest versions of WebKit, which was really frustrating, and we needed to find some way to circumvent that. And according to documentation from WebKit, to circumvent it, there needs to be a user interaction. It could either be a tap, a click, or a use of the keyboard with your website as first party. So in a real attack scenario, we open up a tab using window.open, and then we keep polling the vulnerable endpoint until the user interacts with it, which basically allowed us to circumvent the ITP. And when we started submitting this vulnerability to several bug bounty programs, we noticed that a few of them had similar misunderstanding around them. And we'll discuss two similar common misunderstandings that we found among those programs. A common misunderstanding among security teams of several programs was around authorization code, unaware about its capabilities and how sensitive it is. The misunderstanding was that without the ability to exchange authorization code for access tokens, the authorization code were useless, since exchanging them required application and application secret. While the statement above is true, in a case where OAuth was used for authentication, simply having an access to authorization code was enough to get access to victim's account. Making a request to an authorization endpoint with stolen authorization code with attacker-generated state or nonce value would allow an attacker to authenticate into victim's account. Another common misunderstanding was with regards to state or nonce value and its capabilities to prevent attacks in OAuth. While using state in OAuth is an excellent way to prevent CSRF attacks and to redirect users to where they were before the authentication process started, apart from that, the state really doesn't provide any additional security features. Even if the state value is bind to a token, an attacker can generate a fresh state value, which then can be attached to an OAuth endpoint URL to send to the victim. The resulting token of that request then can be used by an attacker without any issue. The same thing was also demonstrated in our demo video above, where we saw that nonce value a state value did nothing to prevent the attack. Stats. These are some of the stats based on bug bounty programs and reports we made to them. In total, we were able to harvest more than $100K in bounties. The response from the bug bounty programs were kind of mixed. While some programs took the issue very seriously and applied a fix in under 21 hours, which was really impressive, some took months to just understand the vulnerability. And some of the programs also relied on WebKit to come up with a fix. Some programs like Dropbox and Polonix took it one step further by using their contacts at Apple and asking them to come up with a fix. The highest single reward was given by Coinbase, which was also the fastest program to fix the issue. Apple took more than a year, a total of 457 days to come up with a fix, and in the end decided that the bug does not qualify to be awarded a bounty because it does not meet the published bounty categories. And ironically, while this bug in WebKit made so many applications in the internet vulnerable, the Apple's implementation of SSO and OAuth were not vulnerable.
We saw how we can exploit the vulnerability and how severe it could be. Now, let's discuss some fixes as well. As a developer or a site owner, we can use any or a combination of these methods to prevent such vulnerabilities altogether. They're all very easy to understand and implement as well. And the first one is to use post method instead of get, which actually aligns with the practice of never sending any sensitive information over the URL. For example, SAML only uses post instead of get for transporting tokens. And the second one is to use post message for customing communication. These two fixes are also supported by OAuth for OpenID Connect, as can be seen on the image on the right. And they could be specified by a response mode as long as the authorization service supports. However, it's still necessary to disable or remove the support for query and fragment modes. And the most effective one, in my opinion, is the third one, synthetic cookies. It not only protects against this particular vulnerability, but makes almost all kinds of vulnerabilities invisible. Synthetic cookies protected quite a few programs in our campaign as well. Similarly, we have Pixie for OAuth, which makes the exploitation kind of useless because we also need code verifier to make use of the linked code. The other one is to ask for authorization every single time. And Apple did the exact same, and many others too. So they were not vulnerable. And one can also use client-side redirects instead of 302 or 301 in combination with XML options and CSP's from ancestors. Twitter, for example, uses this method of redirect for authorization. The last one is to validate the referrer origin against the client, though we do not recommend using this as it suffers from the same issues as with CSR protection with referrer origin. Browsers also have some mitigation strategies in place to avoid such leaks, though the strategies, however, are specific to CSP. We have something coming up that the strategies do not cover. So for now, let's just briefly go over that. And the violation report now includes the URL of the original request, meaning we only get what we already know. Furthermore, browsers ignore the path component of a source expression if the resource being loaded is the result of a redirect. This is to prevent a leaking of path information, which are demonstrated in Markup's post. The spec also gives an example for easier understanding, but we'll leave it at that. Bypasses and a new Oday. Yep, you read that right. New day, but let's discuss some bypasses before we drop in Oday. After our report, many programs, including Facebook and Coinbase, came up with their own fixes. And their fixes revolve around checking if the user agent is a Safari, and only if it is, they would use a different approach. And for all other user agents, their workflow remains the same. So it seemed a simple change of user agent would bypass the fix. And an obvious place to try it was Request desktop site on iPhones or iPads. Since all browsers and iOS devices must use WebKit as their engine, as Sachin already said, they're all essentially the same. Sending to desktop site did change the user agent. However, it wasn't inherited in subsequent requests. So we tried all requests from a project called HTTP Leaks by Q53, and found that a ping or anchor tag with ping attribute did the work. And we had another bypass. So, but during our hunt for bypasses, we noticed something peculiar. After some digging, we realized that we have already found another Oday. This time, it wasn't CSP, but cross-origin resource sharing, or cross reset. The finding was easy as on the slide here, and we just needed to add a class handler to our fetch request. And unlike the previous one, it doesn't require the rubric to be cross-origin. So yeah, even after our original issue was passed, we found another Oday that was identical to the one we reported earlier. But as always, Apple didn't seem to care much, so it's still unfixed and unpatched. So feel free to play around and report to programs you may find vulnerable. But don't forget to give us a shout. And with that, we're at the end of our presentation. If you have any questions or concerns, reach out to us by Twitter or send us an email. Thank you for listening.